In the second demo, we look at the equation editor. The equation editor builds on the ProMo ontology, which was introduced in the first demo. To start, we need to run a Python code with the name of ProMo ontology equation composer, which opens the logo of software. Once we click on the logo, a table with existing ontology opens and we select demo equation. First, let's look at the different elements in the window. We start from radio variables, which opens domain tree as defined in ProMo ontology with three editing components for each domain: graph, node, arc. Variable aliases opens the same three domain view selection and a new alias table. Index aliases, which open a new window to change notation of aliases. Information bottom, which provides information for user. Compile bottom, which compiles all variables and equations into MATLAB, Python, C++, and it also generates all files currently for variables and relations. It also compiles into LaTeX to show the results, and LaTeX make documentation and help with building. The equation editor is used to modify or enter equations. Now, I'm going to enter a few basic physics equations, as you can see here, into two domains, physical and material database. To define the basic framework of variables describing microscopic system, which leads us to expand more with variables. For this purpose, from the Network tab here, we select our domain of interest, which is physical at the moment. We start to add variables, which are either port variables or defined via an equation. In this example, our port variables are internal energy, entropy, volume, and species mass in mole. Well, we start to add them into state variables classes. And as you may remember, our variable class is defined in node. So I select state to define the variables. The first port variable will be internal energy. Now I can describe. The unit will be kilogram meter square over second square. The next port variable will be entropy with the unit of with description of entropy and the unit of kilogram meter square over Kelvin second square. And state represent the token in node. So index is node here for internal energy, and it's node for entropy. Now let's move on to the next port variable, which is volume. Now the unit will be meter cube, and in this is same. And the last port variables here is number of mole, species, mass in mole with the mole unit, and also the index is node and species. Let's define mass also here. With the unit of kilogram. Same node. That's all with the state variables. So once we define state variables, we cannot change them, and we need to consider that unit and indices cannot be changed once variable is used in an expression. And also a variable may be describing by more than one equation to cover different uses. Now let's move to the effort variables or generalized force. So let's select effort. Once we click on effort, a form in a new window opens, which we can define the equation of pressure, for example. And so let's do that. Pressure, when we hit enter, we can now enter the operation for this equation. We have a few options, variable tables that we can choose from here, indices, and operations. Here for pressure, we need to choose negative operation and partial differential operation, which is partial differential of internal energy over volume. We hit the enter, and once we hit the enter, at which time the right-hand side is compiled and compiler computes the unit and indices, and the result will shows in the window below right-hand side in this here. And now we are ready to define. Definition of pressure. And we accept the equation. The next one is temperature. We repeat the same process. Same operator, partial differential of, but this time internal energy over entropy, and then definition of temperature. We accept, and the last effort variable will be chemical potential, which needs the same operator, but this time partial differential with respect to number of mole. We hit the enter, and we provide description. Chemical, its definition of chemical potential. And we accept. Now we are ready to define enthalpy equation in the secondary state variable classes. So for this purpose, enthalpy will be addition of internal energy plus multiplication of pressure volume. We hit the enter, and so this is definition of enthalpy, and we accept. And finally, we are ready to define mass density into the property for the material database domain. It's rho, and it will be mass multiplied by volume inverse, and then we choose inverse operator from here. We hit enter, and there it is, definition of mass density. We accept, and that's all with the equation. Now I'm going to edit variables for a LaTeX file from each domain. As you can see here, we need to edit this one. And for physical domain, a mu, and that's all. Equations can only be established with already existing variables. And we could also define an alternative equation, for example, for chemical potential here, based off Gibbs free energy. But for this purpose, we would need to define Gibbs first. So let's compile the file and to see the results. Now, as you can see, this is later a PDF result, and then you can see the set of variables we define in physical domain, and also we define mass density in material database domain. And at the end, we can see the list of equation we enter to the system. And that's all with this demo.